Okay, so now we're going to get into the first part of quantum computation and quantum information, um, or at least something inspired by it, expanding more upon the topics they cover. And so right now, all we're talking about is single qubit gates. And well, before that, we obviously have to talk about what the qubit is. I should also specify these single qubit gates will just be the Pauli gates. We won't be discussing anything like the Hadamard gate today. So first, what is a qubit? That's a harder question than it seems. So we know that a normal bit might be just a single transistor or something like that. Doesn't really matter what it actually is because we're just caring about what it theoretically is, and it represents a single value, either a 0 or a 1. You can flip it on or off, you have some sort of electric current running through there. That's your single bit, and that's how we understand pretty much all of computation today, from binary sequences to our basic understanding of a Turing machine, the tape that has values on it that you can adjust is based on this binary nature. A qubit, on the other hand, is not like that. A qubit, a single qubit, is often represented by a sphere, which I will attempt to draw, perhaps poorly. And really, and is notably different because it relies on certain quantum mechanical properties, notably the linear combination or superposition of wave functions. And so if we have a single, I'll just represent this as a normal bit. If this is a normal bit, and we see this is the equation for it, we know that it is always 1 times 0. If we consider the notation of quantum mechanics, then these are always represented. The probabilities are always 0 or 1. If we see, the bit is 0, it's always 0. That's just the way it is. That might be too confusing, weird use of Dirac notation. But if we consider a quantum bit represented by its wave function psi, we can say that it is in a superposition of states with some alpha plus some beta. And these can be complex variables or complex numbers. And so what does this mean, though? And so we see that if this is sort of a sphere, we have the traditional 0 and 1. So this might be 0, the top, and this might be 1. So we have a vector that represents this wave function. So we can say, okay, it represents 0 here, represents 1 here, but it can be anywhere on the sphere. Might be pointing out here, might be pointing down here. An important note is that it's important to perhaps consider this in a largely theoretical sense, because, and trying to gain physical intuition into quantum mechanics is a challenging process, and it doesn't always yield any sort of insight into what's actually going on. And so when we consider the potential here, we think, okay, this seems great. We can represent two values, right? Because this right here might be, some combination of states. And we might say, okay, this is great. This is the solution to everything. Why would we not, what's the disadvantage here? And the disadvantage, I shouldn't say disadvantage, the slightly important thing to consider is that when you measure a qubit or you get information from it, you can only measure one value. So if you say, okay, I'm going to look at the spin, or I'm going to look at the qubit to get, see whether it's 0 or 1, you're only going to get one of these values, either 0 or 1. And so how do we know which value we're going to get? And that's where these coefficients come in. These are the normalizing coefficients and the probability amplitudes. So we have that these squared, or I should say them multiplied by their conjugate in case they are complex numbers, always equals 1. And so this is sort of like the sphere. There's 1 all around. So the radius is 1. And so we have this knowledge here then that we can manipulate the probabilities of measurement. And so that leads to a lot of probabilistic algorithms, but that's something we'll get into later. When we consider what this means, obviously I don't want to go too much into Dirac notation right now, but if we have some wave function and we say it has these coefficients alpha and beta, what does this really mean? Well, this just represents the vector, this, and this just represents the vector here. And so you can see how this is, spin up, or it's pointing all the way to the top of the sphere, and this is spin down, or it's pointing all the way to the bottom of the sphere. And so from this, we can see that we can also represent this wave function just as the vector of the coefficients. And so we have a more compact representation of the same thing. These two are exactly the same. But you'll commonly see this just because it's convenient to understand this as, up, down, 0, 1. And so now we can see, okay, if we have a wave function that's, some part up and some part down, how do we manipulate this? And so there's 3 basic gates called the Pauli gates, which are X, Y, and Z, which have matrices associated with them called the Pauli matrices, which are the Pauli X, the Pauli Y, and the Pauli Z matrix. And so these are originally, related to spin operator, but you'll see them as gates as well. And so what each of these are, so we know these are just well-defined gates that are as presented down here. Don't want to mess them up, so I'm just double checking. And we can see that the Pauli Z gate, right, 0, -1. All of these are pretty common in quantum computing and have very defined operations. And we can really, any single qubit gate can be made that's a unitary matrix. So what does unitary mean? So if we have some matrix U, unitary means that it multiplied by the complex or the conjugate transpose is itself. So we can quickly verify, for example, that the Pauli Y matrix is in fact the unitary matrix by simply doing this operation. So remember that this is the Pauli Y matrix. This is the complex conjugate, because I should erase that. That's my bad. Because we know that the conjugate transpose is we take columns here, make them the rows here, or we take the rows here and make them columns here. So we have this actually same matrix here. So it's and so now we can simply say, okay, row, to get this first value, matrix multiplication, row times column, and we get -1, I times 1 is 1. For this value, we do row times column. We see this column. We see that's 0. We do row times column. We see it's 0. And we do row times column. -1 times -1 is 1. So that's the identity matrix. So that's just verifying that the Pauli Y matrix is a unitary matrix. There's also self-adjoint or adjoint matrices, which play an important role, but that's something for a later date. And so we can see that this is the key characteristics of all quantum gates, is that they have to be unitary, i.e. reversible in some sense. So if we apply Pauli Y gate, if we have our starting wave function, then we apply a Pauli Y gate to it. If we apply a Pauli Y gate again, we'll get the initial vector back. And so we can undo any operations in that sense. But what exactly do these operations do? And this will be the last sort of topic of today, and that is actually applying these operations on them. So we'll actually derive them, not just list them. So we know that the X gate, first we'll see that X, and if we apply this on the parameters, then we can see that, okay, row times column, we get beta, and row times column, we get alpha. So that means that the X gate applied on a wave function transforms this wave function from this into this. So what does that mean in an intuitive sense? This is sometimes called the quantum NOT gate, because if we consider these as just ones and zeros, if we have a pure spin up state, or alpha equals 1, beta equals 0, then we reverse them. That makes it completely spin down, which is the state. So we can see, flipping these reverses this operation. And so next we have the Pauli Y gate. This is a little more complicated, perhaps the most confusing gate, and that is because it acts in a complex way. And by complex, I do not mean complicated. I mean literally the imaginary numbers are operating in the complex dimension. And so if we do this, we can see that this results in row times column, we get -I beta, and row times column, we get I alpha, or we can write this factoring out the I to be -beta alpha. And so this can be represented the same way above. So here the change we can see is that it impacts in the complex dimension, or it's not just real numbers. We're operating in C, not just real numbers of, in this case, dimension 2. And that's, we often separate complex numbers from the quote-unquote real world, but they are in fact very much an important factor here. And last is the Z gate. This will be an interesting one. So if we have the Z gate, which is 1, 0, 0, -1, then we apply it on alpha, beta, you can see that row times column, we get alpha, row times column, we get negative beta. So all this does is change sign of the spin down component in this example. And so what does that mean? This is why it's a little interesting is if we have a pure spin up function or wave function, i.e. 1 times 0, this has no impact. And this makes sense because if you're thinking about these as, you're flipping it around this axis, or you're flipping around the x-axis or y-axis or something like that, we're already on the z-axis, so there's nothing to flip. It's already there, and so that's basically the main three, well, the only three Pauli gates. And so that's going to be it for today. Next, I'll talk about more complex gates, such as the Hadamard gate, still remaining with the single qubit, and talk about the importance of bases and eigenvalues and eigenvectors. And hopefully next time we'll begin some simple programming with Circ, which is a quantum computing simulator. So yeah.